Since friction is common in the motion of an object, we discuss here separately the effect of friction on the energy of the system. This is also the example of the non-conservative force effect on the energy of the system. The work done by kinetic friction can be defined as the work done by kinetic friction WF is equal to the minus of FKD. Okay, where D here is the distance that the object moves. Okay, it means that if we have an object move with a distance D, okay, and it subject to the kinetic friction. It has to be kinetic friction here because the object moves. Okay, and you may say that from the definition of work, we have that W star F is equal to the integral of Ri to Rf of the friction dot dr. But we know for sure that the friction and the direction of the friction and the direction of the motion are parallel but point in the opposite direction. So what we know for sure is that the F K dot dr is equal to the minus of Fk dr. Okay, so we have this equation as the integral of the minus of the integral of Fk dr from Ri to Rf. Also, we know that approximately the kinetic friction is a constant, so we can take this Fk out of the integral. So we have that this is equal to the minus of Fk integral of dr, and the integral of dr here is the distance d. Okay, so finally we have this equation. To be precise, we may have to put the quote symbol word here, and also that's why we have to put this elliptic symbol here. It is because the motion involving with kinetic friction and the work done by the kinetic friction is quite complicated. The definition of work for the friction is more complicated than the other work. The other work from the work from the other forces. Okay, it means that if you want to calculate the work from the friction, it's more complicated than the calculation of the work from the other force. One reason is that during the motion under friction, the object can be locally deformed. The displacement of the point of application of the force may be different from the displacement of the object, as shown in this figure. In this figure, you can see that the friction, we know that it comes from the contact between the object and the surface. For example, this is the system of the book and surface, and the friction happens at this contact. When we slide the book with a distance d, you can see that the contact may move, and if we assume the symmetry between the contact, the surface of the book and the surface of the plane, this, you can see that we may move the book at a distance d, but the point of the application of the first, which is at the point of contact here, may move maybe half of the distance d. This is because we assume the symmetry of these two surfaces. So it means that the motion of the point of the contact of the application of the force is not equal to the motion of the object. Anyway, we know that it cannot be like this forever. After this contact will be broken, and this point may be touched with other point on the surface again. So it makes the mechanism of the friction more complicated. That's why we have to use this symbol. This is the work in the sense that if we look globally on the effect of the kinetic friction, we may be able to define something that's similar to work for the kinetic friction like this, and we will see the effect of these things, which we call it the work, but to be precise, it's not exactly the work as we have defined so far. We expect that this term work and this definition is valid if the distance that the object moves is quite larger than the size of the deformation, which is always the case. We can use the usual definition of work for the friction as in this equation if the distance that the object moves is quite larger than the size of deformation. Now, let me discuss the effect of the kinetic friction. If we assume the object as the system, the object, for example, in this figure, this book, only the book, is the system. The work kinetic energy theorem can be written as work kinetic theorem. The work kinetic theorem can be written as the work from the other force plus the work from friction must equal to the change of the kinetic energy. So this is the work kinetic energy theorem. Now, if we substitute the expression for this WF, we must have a work from the other force minus FKD is equal to the change of the kinetic energy. Okay. This equation tells us that if you do work to the system, in this case the book, you have to pay something to the friction, and the effect of the work is reduced. I mean, the effect of the work done by the other forces is reduced because of the friction. And once you pay for the friction, the rest of your effort go to the kinetic energy.